Today I'm going to talk about like the deep learning things, the all-in-one AutoDL vision software from model to data-centric features. So I'm Hong-Sung Lee from Neurocle. So today I'm going to talk about so many things about like model-centric and data-centric. Let me go through one by one. But before I start, I want to give you one question. What do you think of the end goal of the deep learning vision inspection? Because nowadays, many people are talking about deep learning, AI, but of course, it's a big trend, but why should we use this? It's not a mandatory, actually. The reason we want to use deep learning in this machine vision area is, of course, to maximize the inspection accuracy. Without deep learning, without AI, sometimes for some project, we cannot maximize the accuracy. So that's why many people are talking about deep learning and AI. Then, we have to think about how to maximize the accuracy with deep learning. That is the most important question we have as a deep learning software suppliers. So to solve these problems, actually, we can think of two ways. One is the model-centric way, and the other is the data-centric way. So today, I'm going to talk about these two things at the same time. For the model-centric features, I'm going to talk about auto deep learning, auto DL models. And then data-centric things is about the labeling things and the synthetic data things. So let me go through one by one. So firstly, the first model-centric feature is the auto deep learning algorithm. So auto deep learning algorithm is actually optimization algorithm when you train the models. So nowadays, many people are just using open sources, well-known model, but that is not optimized for your training data. So if you have an easy task, you can just solve it with that. But if you have a very difficult project, it's very difficult to maximize your accuracy. So that's why we develop auto deep learning algorithm, which optimize three things: deep learning architecture itself, hyperparameter of the architecture, and lastly, data augmentation. So thanks to this auto deep learning algorithm, we can optimize your deep learning model based on your training data so that we can maximize the accuracy of the model. And of course, another good thing is that non-expert of deep learning can easily create the best performing deep learning model because they can just rely on our optimization algorithm. So based on this auto deep learning algorithm, we are providing 9 types of the different deep learning models, from basic classification segmentation to like the deep learning based OCR, patch classification for high resolution, and 2 different types of the anomalies. As you can see, I'm going to go through 4 models today: patch classification, GAN model for the defect generator, and 2 different types of the anomalies. So let's go to firstly talk about 2 different types of the anomaly models. Then, why should we use these anomaly models? Because in the real world, in the manufacturing lines, it's very difficult to gather some defect data, and it's very difficult to gather well-balanced defect data. Because in some cases, some type of defect just occur maybe once in a year, once in 6 months. In that case, we cannot train that defects. That means we cannot train the well-performing deep learning models. So we have to solve this problem. And also, normally, if you only have a regular type of the defects, you can just go with the conventional rule-based algorithm. But the reason you want to apply the deep learning is there are so many non-standard and irregular defects. So to solve this problem, maybe we need anomaly models. So normal models, what we call the supervised learning, we train both normal data and OK data and NG data. However, for these anomaly models, we only train the normal data. That's why we call it unsupervised learning, or some people say it's a weakly supervised learning. So we only can gather some OK data and train the anomaly models. Then the model will find out abnormal cases. So this is a good thing of the anomaly models compared to the conventional, like the supervised learning. So we provide 2 different types of the anomaly models. One is the anomaly classification, and the other is the anomaly segmentation. So the result is very similar, like supervised classification and supervised segmentation because anomaly classification shows the heat map, which can call class activation map, and anomaly segmentation shows the exact blobs on the defects on the surfaces. So the good thing of this anomaly is you can train even when the defect data is insufficient. And also, you can minimize your resources for the model training and the image labeling as well. Because we train only with OK data, that means we don't train the defect data. So it also minimizes your training time. And also, we don't have to label for the defects because we only have OK data. So this is another good thing of the anomaly models. So we have many use cases of anomaly models. This is just one example. So we want to find out some missing pallet under some logistics centers. Normally, they have to have like 5 pallets, but sometimes, very rarely, they just put 4 pallets in some way. So with this anomaly detection, anomaly classification, we can improve our accuracy from 48% to almost 100%. Is one of the use cases we can share. The next thing we want to share is the patch classification model. So I think you know the normal classification model, but when we train the model, classification model, the basic unit is just the image itself, so that sometimes if you're using the high resolution data, then you have to resize the images into maybe 1024 by 1024. But if the defect is too small, then maybe we lose some data, we lose some defect information. So in that case, we have to think about how to deal with this situation. And also, we can just think about, OK, the image is too large, then maybe we can just divide it into patches like this. But however, if the defect is a little bit large, then maybe defects also occur into the borderline of the patches. Then also, it's also hard to detect. So we have to think about how to deal with these problems. So patch classification is overcoming this kind of limitation of the classification when we are using high resolution data. So what we do is, of course, we divide patch by patch, but internally, there's another algorithm to make it balance, even if the defect is located between the borderlines. So this is how we work with patch classification. You can do the labeling with patches. Just click it or drag. Or you can make it much faster like this. So you're going to drag and do the label on the defect patches. I think, yeah. And then yeah, it's done for your labelings. So you can do the labeling as like the segmentation, but it's a classification. So when you're using this patch classification, another good benefit is it's very easy to integrate. Because without this our patch classification, you have to use some pre-processing or post-processing to do the integration with the high-resolution data for the classification. But this patch classification includes all the pre-processing and post-processing of the patches. You just call our model, and then you can get all the result at the end. So we also have many use cases because if you're using high-resolution data, then patch classification is very useful. One example is detecting the wire defects, because they want to use a very high-resolution camera, like line scan camera, so that we have to detect the defects on the wires. So in that case, like the wires are a little bit in the strange way, so we cannot use the segmentation. We have to use the classification, and then this patch classification helps a lot. So thanks to patch classification, we can increase our accuracy from 66% to almost 99.9%. So there are many use cases with the line scan camera of our patch classification. And I just talked about like two model-centric features. One is anomaly models, and the other is the patch classification. Let me go to the data-centric features. And first thing is the synthetic defect image generator based on the GAN model. So why we need this kind of image generator? Because normally in the manufacturing lines, we are lacking of the defect data. It's very easy to gather some OK data, but sometimes we are having a hard time gathering some defect data. So that's why we are thinking, why don't we generate the defect based on the deep learning models? So we are using the GAN model. GAN stands for the Generative Adversarial Network. So in the GAN model, there is a two network. One is the generator, and the other is a discriminator. Generator just generates the new data, and discriminator will discriminate. This is very similar with the real data, or this is a little bit different from the real data. So the model will find out, model will create the new data, which is very similar with the real data. So this is how a GAN model works. So to teach some types of the defect, we need at least 10 defect data. So with the 10 images of defect, we can train the GAN model. Then after you train the GAN model, we can use the OK data and then put the defect stamps on the GAN images, OK images, and then a GAN model will generate some new defect images as like this one. This is how it works. Yeah. And also, sometimes, if GAN model is a little bit heavier model, as I mentioned, because it includes generator and discriminator, right? So that it's also difficult to use a high-resolution images. So we also have a patch mode to this GAN model, so that even if you have a very small, tiny defects with high-resolution data, you can use a GAN model. This is another benefit of ours. And also, as I mentioned, we only require 10 defect images. So you can easily create some GAN model with little amount of the data. And also, we provide a stamp tool. So you can put these defect stamps on the OK data, on the surface of the OK. Then these defect stamps will be very similar with your original defects. So you can easily create very similar artificial defects with real defect data. So by using this GAN model, we can generate the synthetic data. And of course, compared to the, how can I say, initial data set, without this synthetic data, we can improve the model's accuracy, like up to 97% on this case. And lastly, I want to talk about some AI-based labeling tools, because nowadays, many people are using large amount of data, more than like 10,000 data images. In that case, labeling is a very, very time-consuming job for you. So we invented AI-based labeling tools. So there are many AI-based labeling tools, like we call it like the magic wand, auto-selector, or keyword labeler. Let me introduce first about the auto-selector. Sorry. Sorry, I think the video doesn't work. So anyhow, yeah, auto-selector is like, it works? It doesn't, something like, yeah. So it's based on our foundation model. If you just click and drag, then it can easily tell where you have to do the labelings. I think if I can show the video, it's much easier to understand. But yeah, if you're interested in, please come to our booth. I'm going to show it later. So auto-selector is like you just click or drag, then the labeling is done very automatically. This is the biggest benefit of auto-selector. And we also have the keyword labelers. The video doesn't work again. Yeah, you just type in the keyword. Like I want to find out some drops on here. You just write down the water drop. Then our foundation model will find out the water drop on the images automatically. So thanks to this auto selector or keyword labeler, you can easily do the labeling without any manual labeling tools. And lastly, we also have auto labeling. This concept is a little bit different from the previous one, because auto selector and keyword labeler, we are using the foundation model, but auto labeling is like this. So just assume that you have like 10,000 data. And then maybe you can do the manual labeling for 50 images or 100 images. And then we are going to train the one deep learning model for the labeling purpose. And then once you create one deep learning model, you can use this deep learning model's features to do the labeling for the rest of the 9,900 images. This is the concept of the auto labeling. And it's also very powerful when you have a large amount of the data. So what we do is we try to minimize your resources for the labeling, because sometimes labeling is really, really time-consuming job. So let me summarize my presentation today. So we are providing auto deep learning vision software to maximize your accuracy. Some problems here. Yeah, so and then we have two software package. One is the training software, and the other is the runtime library. So with our training software called NeuroT, you can upload your data, upload your images, manage your data, and then do the labelings, and then train the model, and then check the model's result and performance. And once you are satisfied with the model's result, you can easily export that model, and you can integrate this model with our runtime libraries. So this is a concept of NeuroT and NeuroR. So T stands for the training software, and R stands for the runtime libraries. So all these, our software package is based on the auto deep learning algorithm, as I mentioned, which optimize deep learning architectures and hyperparameters automatically. So even you're not the deep learning expert, you can easily creating the best performing deep learning model just with one click. So I just assume some typical cases. So if you don't have defect data, you can think about using our GAN model, which generates the synthetic data. If you are using very high resolution images, then you can think of using our patch classification. And lastly, if your defect type is really, really irregular, then maybe you cannot go with the supervised learning. Then we also provide 2 different types of the anomaly models, which solve your problems on the real manufacturing site. So I just summarized my presentation today. Our company name is Neurocle from South Korea. Our booth is over there at 8B11. So if you have any questions, unfortunately, I cannot.
So do we have questions from the audience? No questions from the audience, but I have a few questions. It's very interesting. So the unsupervised models are the ones that you're calling anomaly models, right? The anomaly models are called anomaly models, but the images that are used to train those models are not actually of anomalies. They are of the ones that don't have the anomalies, right?
I didn't get it clearly. What do you mean?
You said that in your you make your anomaly models with the help of the good images, only good images.
Only good images, yes.
And not OK images.
Not OK images.
So those images, they don't actually contain any anomalies. They are not. They are the ones that do not have anomalies. They are the right data.
Yeah.
But the models are called anomaly models, even though they are trained with good images.
Yeah, because anomaly models learn the boundary of the good images.
Okay.
Because if there's image data, we can calculate this image data and then put this image data into some very multi-dimension space. And then once we embedding those images into those OK images into space, then we can tell where the boundary is, right?
Okay.
Once we calculate this boundary of the OK data, then if there's new images come, then we can embedding once again and then see whether this is in the boundary or out of boundary.
Okay.
If this is in the boundary, we can consider it as a OK. If it's out of boundary, we can consider it as a anomaly, abnormal cases.
Yes, exactly.
Yeah, this is how it works.
And then how do you use the anomaly models for classification? Because that is also what you said, right? You're using the anomaly models to classify the anomalies, like the type of defects that can be there or which look similar or something like this. You can classify the types of defects using the anomaly models.
No, by using anomaly classification, we only can classify whether this is good and bad. If you want to classify the defect types, then of course we have to go with a supervised classification.
Okay. And then you said that for your supervised classification as well, then you have the other side of the software suite, which can generate images that can be used by the supervised learning algorithms. So for the supervised learning algorithms, you need labeled data.
Supervised learning?
Yeah, for the supervised learning.
Yeah, we do labeling, whether like we tell this image is class A, this is class B.
Yes, exactly.
We do the kinds of labelings, yeah.
So those labelings, I mean, that labeled data is needed for the supervised learning to work, right?
Yes.
And you said at the later point in time in your presentation that that AI can also be used to generate these defective images.
Yes.
To label these defective images, and then you can feed it to the supervised learning, and then that's it, right?
You're right. So if you only have 10 defect images, of course, we have to do the labeling for those 10 defect images. But we can train GAN model with these 10 defect images. Then we can generate a lot of the synthetic data, defect data. Yeah, you're right.
Great. Thank you. I'll meet you at your booth.